Namaste everyone. A plano-convex lens of thickness 6 millimeter is placed on a table with its plane surface upwards. Now its thickness appears to be 4 millimeter. On reversing the lens, its thickness appears to be 30 divided by 7 millimeter. Calculate the refractive index of the material of the lens and its focal length. Of course, it looks to be very simple and very short problem, but it involves everything whatever you are getting in refraction in a curved surface, lens maker's formula. So you'll have to use everything here. But problem is simple actually. You will have to use all the concepts. No, when the plano-convex lens is placed with its plane surface upwards. So the first part, that is very interesting now. When it is plane surface upwards, its thickness appears to be 6 millimeter. Now you can use the formula refractive index equal to real depth by apparent depth, because you are looking from the plane side. So n is equal to refractive index, n is equal to real depth by apparent depth formula. Remember, this formula holds good only when the refraction is occurring at the plane surface. Otherwise, you can't apply this formula. If you are looking towards for example, whenever you look into an air bubble inside a glass sphere, it appears to be shifted up. But in that case, you can't use this formula since refraction is not occurring in a plane surface. If you are looking into an air bubble inside a glass sphere, the refraction is occurring in a curved surface. So you can't use this formula. But now this is possible. So on the table, even though the curved surface is like this, on the table, this is in touch with the table. This point appears to be here. And whatever the rays of light that have come from here, one ray of light might have moved like this. Another ray of light after refraction through the plane surface might have moved like this. So they appear to come from this point. So this is the object and this is the image. Whatever it is, even though this surface is curved, refraction has occurred through the plane surface. So you can use this formula, no problem at all. So you can write n is equal to, it is given that the total thickness of the plano-convex lens is 6 millimeter, and it appears to be at a depth of, they have given this depth also, it appears to be at a depth of 4 millimeter from the surface. So I can write real depth by apparent depth. Real depth is 6 millimeter. This is 4. So millimeter gets cancelled. I need not write it. So refractive index is 1.5. Easily we have got it. Now we will go to the second part. That is very interesting. On reversing the lens, its thickness appears to be 30 by 7 millimeter. Of course, the real thickness remains the same, 6 millimeter. Now, when you reverse the lens, the whole thing gets reversed. You can't use this formula now, because when you put it on the table like this, suppose this part of the table, suppose you have something written on the table, it appears to be somewhere here. And if at all it appears to be somewhere here, then it is not because of the refraction at the plane surface, it is because of the refraction at the curved surface. So how to solve this now? Now I will change the diagram. I will make it very close to the refraction at curved surface so that you can apply the formula easily. So the diagram will be like this. Okay. So I will do it like this. I will look into the plane surface from the, okay, I'll draw it again. So the plane surface, this is the plane surface, and this is the curved surface. I look into the plane surface from here, like this. So let us assume that the other plane surface is covered with a paper. Whatever is written on this side, it has to be observed from the curved surface. As if you look into the that surface of the table, this surface of the table through the curved surface, the whole thing appears to be at a height of some 7 by 3, something, it is 30 by 7 millimeter. It appears to be at a depth of 30 by 7 millimeter. Actual depth is 6 millimeter. So how to interpret it here now? So if something written on the plane surface appears to be somewhere here, how is it possible? Let me draw one principal axis. Now any object here, suppose there is a mark here. The ray of light from here must enter, of course, any ray of light passing along the principal axis passes undeviated. Another ray of light which is incident like this, it bends away from the normal like this, and it appears to be coming from here. So this appears to be the image. So this thickness from the surface, from the pole, is 30 by 7 millimeter. This is 30 by 7, and the object distance from this pole is the thickness of the lens itself, which is 6 millimeter. That's all. So an object here, which is just on the flat surface, appears to be here. That is the image. Now all distances are measured from the pole of the curved surface. Pole to I is the image distance. Pole to O is the object distance. Now we have got it. So this is the ray of light which is incident. Another ray of light along the principal axis passes undeviated. So this refracted ray and the original one meet here. Now you have the formula: refractive index of the medium where incident rays are present by negative of the object distance plus refractive index of the medium where refracted rays are present divided by image distance. Refracting medium refractive index minus incident medium refractive index by radius. So if I can use this formula, what is N1 and N2? N1 is the refractive index of the medium where incident rays are present. Where are the incident rays? Incident rays are here. Already we have found out that refractive index. It is here. You can use it. What is the medium where refracted rays are present? Refracted rays are here. Incident rays are here. So refracted rays, refractive index, I can use it as 1. So 1 is N2, the medium where refracted rays are present, the medium where incident rays are present. So N1 is 1.5. Now, where is the object distance? Remember, all these distances have to be measured from the pole. So when you measure the distances from the pole, you have to go like this. You have to measure the distance opposite to the direction of incident light. So all the distances are negative. Even the radius of curvature is also negative. So now our job is to find out the radius, because if you want to know the focal length, you must have radius. So let us substitute for this formula. Refractive index of the medium where incident rays are present, that is inside the sphere itself or plano-convex lens itself, that is 1.5 by negative of object distance. Object distance has to be measured from the pole to the object. That has to be done by moving in the reverse direction as the incident light. So it is -6 again. This minus sign is in the formula itself, and -6 is another minus, because the distances are measured opposite to the direction of incident light. Incident light is in this direction. Okay, plus refractive index of the medium where refracted rays are present, that is 1 by image distance. Image appears to be at 30 by 7, whose distance is also measured opposite to the direction of incident light. So it is minus 30 by 7 because it is also opposite to the direction of incident light, is equal to N2. N2 is the refractive index of the medium where refracted rays are present, incident rays are present. Radius of curvature. Radius of curvature is this one. It's a radius of curvature we don't know. So we get it as the formula gives the answer. So this will be 1.5 by 6, because minus of minus is plus, minus 7 by 30. 7 comes to the numerator, is equal to minus 0.5 by r. Now I will multiply by and divide by 2 wherever I have fractions. 2 multiplication, 2 division. That gives, or I can write it as 1.5 by 6 is 4 times. 4 times minus 7 by 30 is equal to, I can multiply here by 2 and divide by 2. So that becomes minus 1 by 2r. So I can take common denominator here. 60 as common denominator is okay. 4 15 times 32 times 14, it is equal to minus 1 by 2r. So r is negative. Okay, no problem. This comes to 1 by 60 is equal to minus 1 by 2r. So r is minus 30. Okay, minus 30. I think everything is in millimeter, so it should be 30 millimeter. Because what we have substituted this 30 by 7 and 6, everything is in millimeter, so minus 30 millimeter. Yes. Once you get R, you can use R equal plus or minus depending on how do you use the lens. Now they are asking you to find out. So calculate the refractive index of the material of the lens and its focal length. If you want to find out the focal length, you should use lens maker's formula. We will use it. Lens maker's formula. Okay. So I'll keep the lens as it is, plano-convex. You can keep it anyway. So this is radius R1, which is equal to infinity. And what about this? The center of curvature of this surface lies somewhere here. So you'll have to measure the distance in the opposite direction. So this is R2. R2 has to be taken as 30 millimeter. That is what we have measured just now, minus 30 millimeter, because the center lies in the left-hand side. So minus 30 millimeter. So what is focal length? Focal length is 1 by f, lens maker's formula. Refractive index of the lens minus surrounding medium, refractive index of the lens by refractive index of the surrounding medium minus 1, n2 by n1 minus 1. That's what we write usually. I'll write refractive index of the lens by refractive index of the surrounding medium minus 1 into 1 by R1 minus 1 by R2. 1 by focal length of the lens is equal to refractive index of the lens 1.5. Surrounding medium, we will take it as R minus 1 into 1 by R1, 1 by infinity, minus in the formula by 1 by R2, minus 30. 30 millimeter, of course, focal length will be in millimeters. So 1 by F is equal to, this is 0.5 by, this is plus 1 by 30. Yes. So this is 1 by F. 0.5 can be written as half, 1 by 60. So F is equal to 60 millimeter. This is the answer. Focal length is 60 millimeter. So you can put it in centimeters also, no problem. So we have found out focal length, we have found out refractive index of the material of the lens. So the only thing we have to take care here is when you are using the plane surface for refraction, that means when you are looking from the plane surface side, you can use this formula. When you are looking from the curved surface side, you have to use this formula, refraction at curved surface, not real depth by apparent depth. So this is the final answer, 60 millimeter. Thank you.